let's see, last time we left off are the types. It's like I've just shown you the sort of the basic form for the equation. And so today we're going to go through the different types of decay. I list them here. We can have alpha, beta, or gamma decay. Beta will actually have three different types: beta positive, beta minus, and or beta plus, beta minus, and electron capture. But they're all basically the same, or they're all very much the same. The way that you approach them each is just sort of how you look at this equation. And we have this chemical equation or this nuclear equation, and we have a couple rules that we'll need to follow for all of them. And I'll show you how we apply them in particular equations. But we have two rules. The first is that the number of nucleons is conserved. Remember on our nuclear notation, we had X, A, and Z. Which one is the number of nucleons? Is it A or Z? All right, it's A. That's the bigger number, right? This is the number of nucleons, and that includes the number of neutrons and the protons. So A is conserved. That means the number of nucleons in the parent nucleus must equal the number of nucleons in the daughter nucleus plus whatever nucleons you have in other particles. So we'll see that with alpha particles, they carry a couple of nucleons, or four nucleons in fact, and so we'll need to include those. But I'll show you that with alpha decay. And then the second rule is that the number of protons must be conserved. Remember, the number of protons, that's the atomic number, that's Z. So the number of protons on the left-hand side of the equation has to equal the number of protons on the right-hand side. Same for the number of nucleons. So the sum of all your A values on the left-hand side has to equal the sum of all your A values on the right-hand side. The sum of all your Z values has to be constant. So those are the only two rules. They're pretty basic. You will need to know sort of what happens in each of the decay processes, and I'll go through them now, and then I'll summarize them all. We'll practice some different questions like you'll see. Let me go and start up the clicker base, actually. Look at alpha decay first. Alpha decay. So an alpha particle is a helium nucleus, a helium-4 nucleus. It has two protons, two neutrons, two neutrons. So our atomic notation for the helium nucleus is 4, 2. So this is an alpha particle. Although we often call it radiation, even though it's not technically radiation, like it's not radiation in the same way that light is radiation, but it is a particle that travels at high speed. So this is an alpha particle. Sometimes, not in our class, but sometimes you'll just see this as the Greek letter alpha, but not in this class. Okay. Alpha decay occurs in a lot of different cases. So let's look at the decay of 242 plutonium. So 242 plutonium. That means it has 94 protons and 242 protons and neutrons. Notice it has a lot more neutrons than it has protons. Remember we talked about how if they have unequal numbers of neutrons and protons, that makes it unstable. So here, this is a really big nucleus that has a lot of neutrons in it, right? If it had the same number of protons, then this value would only be like what, 188. So it has like an extra 60 odd neutrons in its nucleus. Really big nucleus, that means that strong nuclear force can't hold it together because the strong nuclear force only acts over very, very small distances. If your nucleus gets too big, that strong nuclear force can't hold it together because it just can't act over such large distances. So let's imagine that I have this decay equation. It's going to decay into something that has helium 4-2 in it. And I want you to just try to fill in this blank. I'll do a clicker question. We're going to have A and Z. First of all, I want you to tell me what A is. So we'll do one question and tell me what is A. But go ahead and try to fill it in on your own. Right? Fill in what should be here, A and Z, for the values A and Z. And then we'll look at the periodic table and figure out what is the chemical element for that. So plutonium is decaying to some element, some new element, that that will also decay into a, it's going to decay into some new element plus an alpha particle. So remember your conservation rules. Let's see, for the value of A, let's do these options. All right, so you can go ahead and click in for that. What should be the appropriate value for A? On the upcoming test, you'll have several chemical or nuclear equations like this, and you'll just need to tell me what is the element, what is the atomic number, what is the atomic mass number. So in this case, I'm looking for A. All right, just a few more seconds. I'll stop at, say, 35. Okay, awesome. A is right. It's 238. Because I look at my conservation rules, I know that 242 must equal to something plus 4, and that something is going to be 238. All right? Let's see. Why did the tomato turn red? Have I told y'all that one? Yeah, why did the tomato turn red? Because he saw the salad dressing. You get it? Salad dressing. Okay. So my atomic, my value here for A is going to be 238. All right, what is the value for Z? So let's try this now for Z. The second question will be what is Z? What is the value for Z? All right, I'll stop at 30. Okay, awesome. E is right. Z is going to be 94 equals some value Z plus 2, so that has to be 92. So E is the right answer there. Mark that right? Yeah. All right. Now we can also look at our periodic table. Let me pull one up for us, and we can determine what is the element that's represented here. Do y'all know what the 92nd element is? Hey, very good. Do you just know that, or? Oh, it's in the book. Okay. Yeah, so if we look at our periodic table, uh, 92, wasn't it? Was it 92? It's down here at the bottom. It's uranium. Okay. So stuff like that for the test. Be able to determine what is the daughter nucleus, what is the atomic mass number, what is the atomic number. Okay. I'll give you a periodic table. I'll probably just print it out and put it on your test. All right. Um, all right. Good job. So this would be uranium. U. All right. You also need to know what is alpha decay, what is an alpha particle. An alpha particle is just a helium nucleus. It consists of 2 protons and 2 neutrons, giving it an atomic mass number of 4. 2 protons, 2 neutrons equals 4. All right. Beta decay is a little more complicated. I think you had a quiz question about alpha decay, right? Yeah. So alpha decay is fairly apparent because it's always going to have this thing in it. So I might give you an equation like I did on the quiz and just ask you what type of decay is this? And if it has that helium nucleus, you'll know always that that is alpha decay. All right. Beta decay is a little more complicated because you have 3 different types of beta decay that are all similar but a little bit different. Beta decay, this is often used with the Greek letter beta, so I'll just write it out as beta. Um, you have beta minus, beta plus, and electron capture. So 3 different flavors. And actually, electron capture is different from beta minus and beta plus because instead of emitting a particle from the nucleus, you're actually taking a particle from the inner orbitals of the electrons. So you're stealing away an electron and forming with the proton, making a neutron out of that. So the electron capture is a little bit different here. I'll abbreviate electron capture just to make it easier as EC. You have beta minus, beta plus, and electron capture. Um, see, let's look at this decay chain. So if I start with a neutron, this is the neutron particle. I end with a proton. That's a proton plus an electron. So this is an electron. We talked about this earlier, but my Z number for an electron is -1, and so that denotes the charge of the electron. Plus a neutrino. We'll talk about those in just a bit. So this is our electron, or this is a beta minus particle. So in our parent nucleus, we'll start with a neutron, and then that neutron will turn into a proton by emitting an electron, or a beta minus particle. It'll emit that beta minus particle, and then it also emits a neutrino. More about that in just a bit. You'll just need to know sort of what is a neutrino and the role that it plays. So the beta minus is the same as an electron. Has the same charge, same mass. Um, and here actually I'm sorry, I meant to draw a bar over it. This is an antineutrino, not a neutrino. It's an antineutrino. Neutrinos have no charge. You can tell by their name, right? Because you have this part, which means neutral, so it has no charge. Who knows what eno means? What does that mean? I think it's Italian. I'm pretty sure it's Italian. Bambino. You know what that means? It's like small, right? Eno means small. So here, neutrino is just a really small particle that has no charge. It's like a small neutron, a very small particle with no charge, very small mass and no charge at all. Don't worry about the anti versus regular neutrinos. It has to do with the spin of the particle. which has to do with sort of the basic properties of it. But for every neutrino, you'll also have an antineutrino. Don't sweat it though. Just sort of know that a neutrino is a very, very small particle that has no charge at all. The neutrinos are important because they help us to account for lost energy and momentum. So back in the mid 1900s, when they were studying this and developing all these ideas for how nuclear decay processes work, they found that there was just missing energy in their equations and also missing momentum. We didn't do momentum, but you can think of it in a similar way as energy. And so they developed this idea of the neutrino. And at that time, they didn't really know that it existed, but now we do know it exists, and they're detected, from all different sources, especially the sun. The sun produces a lot of neutrinos that come towards the Earth. They don't really interact with much, so they don't really affect us, and they're actually fairly difficult to detect. I think your book talked about how they detect neutrinos. Do you remember if they did? No. Well, there are observatories all around the world to detect neutrinos. They're usually really, really big. So, like in Japan, they have this big tank of water that's, I don't know, probably 10 times the size of this room with a bunch of photomultiplier tubes. Photomultiplier tubes are used to detect photons. And when these little bitty neutrinos go through the water, every once in a while they'll interact with the water and they'll emit radiation. They have other big arrays like out in New Mexico and around the U.S. that are spread out over many, many acres. In the South Pole at Antarctica, they actually use the entire South Pole as a detector. When the neutrinos enter into the ice, sometimes they'll emit light, and then they have these balloons or satellites up over Antarctica to detect that light. So there are different ways to detect neutrinos, but really for this purpose, all you really need to know is that they're itty bitty, they're small, and they have no charge at all. Also that they do help to account for this lost energy and momentum. I do have a video about neutrinos. It's just sort of for your own interest. I think it's interesting. Let's watch it. Okay, let's look at some examples of beta minus decay. So this is a beta minus decay. I start with carbon 14. It has 6 protons, and it decays to, not carbon, nitrogen 14 plus a beta minus particle. That's this 0 minus 1. Remember, this is basically an electron, plus my antineutrino. Let's see, what is this going to be? What is my value here for Z, my atomic number going to be? Well, you know that if this is carbon, what is this going to be? Right, this is going to be 7. I can look at my equation. I know that these values have to be equal. So if this is 6, this is minus 1. Remember, this doesn't have any charge at all, so I could put a 0, 0 here. Then this has to be 7, because 6 is equal to 7 minus 1. You can identify the beta minus decay by the beta minus particle. Right, this is a beta minus particle. It is an electron, but we call it a beta minus particle because it's beta minus decay. In contrast to that, we see beta plus decay. And as you can probably guess, really the only difference between this decay and this decay is going to be what in this equation? What would you guess if you were to guess right now? The what now? Okay, all right. All right, I'm going to have a plus 1 instead of a minus 1. So beta minus has a minus 1. For beta plus, this is going to be plus 1. All right? So our basic decay is I'm going to start with a proton. I'm going to go to a neutron plus a beta plus particle, which is going to be 0 plus 1, not minus 1. And then instead of an antineutrino, I'm going to have a neutrino. Don't worry about the neutrino bit. Uh, in fact, don't really worry about the neutrinos that much at all, but you will see them on the equation. All right? So an example of that would be, say, oxygen 15.8 is going to decay to something plus my beta plus particle plus my neutrino. You'd be inclined to say that this is a proton, but it's not exactly a proton. It's called a positron. It's an electron, but with a positive charge. It doesn't have all the mass of a proton. All right, what's going to go here? What's my value going to be in the bottom? It's going to be 7, right? Because I have an 8 here, I have a plus 1 here, so I have to have a 7 here. And up top, it's going to be what? 15. Right, so I'll have a 15, 7. And let's look at our periodic table. See, what is that going to be? Nitrogen, right. So this is going to be nitrogen. Those sort of things you'll see on the test. Being able to identify beta minus, beta plus, alpha decay, and then also being able to tell what A, Z, and the element are. That's not that hard, right? No, y'all can do that. But also stuff like we had on the quiz, you know, as usual with the test, go through the chapter, but you'll see several of these type things. Okay, notice our conservation rules are obeyed. So our conservation of A is obeyed. I have 15 equals 15 plus 0. And then my conservation of Z is also obeyed. I have 8 equals 7 plus 1. The neutrino has 0 and 0, so we don't even include it. All right? Little bitty mass, no charge at all. And then we have electron capture. Gosh, we're almost done. So electron capture is sort of in the same category as beta decay, but it's a little bit different. I think it's kind of cool, actually. Electron capture. In the electron capture, the nucleus captures an electron from one of the inner orbitals. So remember, in our shell model of the atom, we have this positive nucleus, and then we have these orbitals. There are certain numbers of electrons. I think we decided there were 2 electrons on the inner orbital. What the nucleus will do is it'll grab one of these electrons and bring it into the nucleus. That's called electron capture. The electrons then will all sort of reconfigure themselves, because then it'll become unstable, and so you'll have this cascade of electrons that will fall down to those inner levels. But for what we're concerned about, we're just worried about this electron is the nucleus reaches out and grabs this electron and brings it into the inner nucleus. All right. The electron combines with a proton. That's a proton to form a neutron. Let me write this out in words just in case. So this is my electron. It combines with a proton to form a neutron. Remember, the neutron we said has a mass that's equal to that of a proton. An electron has a mass that's so much smaller than the proton. It's like it doesn't even matter. It's like 10,000 less, 10,000 times less the mass of the proton, or 1/10,000th the mass of a proton. All right, so if we write out our basic equation, it's going to look like this. I have a proton plus an electron I'll let you finish that off. What does that turn into if I have a proton and an electron? What do a proton and electron form into? A neutron. Do y'all remember how to write the notation for a neutron? So if I'm writing n here for my little n for my neutron, what are going to be the numbers next to it? 1 and 0, right. And you can see that here. 1 plus 0 is 1. 1 minus 1 is 0. So my notation for my neutron, I gave this to you last time, but it looks like this. 1 and 0. It has mass but no charge, so the atomic number is 0. And then this is also going to form a neutrino. All right, so our equation looks like this. Um, this is just an example of beta plus decay. If I start with beryllium 7, beryllium has 4 protons. It captures an electron. What is it going to form? All right, let's look at our periodic table. Is it 4? Oh, yeah, there it is. So, zoom out. What is the beryllium going to form? What is going to be the daughter nucleus? Let's do this as a clicker question. Is it going to be A, lithium? B, will it stay as beryllium? Will it be C, boron, D, carbon, or E, nitrogen? What will the beryllium, what will the daughter nucleus be? Did y'all get the equation that I wrote down the first time? Let me bring that back up, okay? We'll come back to this. I'll show this back to you. But so this is our equation. I have beryllium. It captures this electron. I want to know what now is the daughter nucleus. I'll go back to the periodic table in just a second. All right, can I go back to the periodic? All right, is it A, lithium, B, beryllium, C, boron, D, carbon, or E, nitrogen? Which one of those is the daughter nucleus? All right, we'll stop at 115. 115. Okay, awesome. Lithium is right. If we go back to our equation, um, I'm going to have 7 up here, but I'm going to have 3 down here because the 7 and the 0 add up to equal 7. My 4 and my minus 1 add up to equal 3, and this is lithium. It is the third element. And then also with this, I'm going to provide a neutrino. Let's see. You can tell this apart from the beta minus and beta plus. What is the distinguishing feature for this one in comparison to the beta minus and beta plus? If I were to ask you, what type of decay is this, how would you know that it's electron capture? Huh? It's what's at the end. Right, yeah. So in the others, I always produce a beta particle. So in the others, my proton or my positron or my electron, that 0, positive or minus 1 e is on the right hand side. But for electron capture, it's on the left hand side. And so that should stand out to you. If you see this electron on the left hand side of your nuclear equation, then that should put off in your mind that, oh, this is electron capture. You will have to identify the different types of decays. I'll give you an equation and ask you what type of decay is this. There are only 4, so these are probably the hardest to tell apart. The beta minus, beta plus, and the electron capture. Beta plus is easy to see because it's the only one that actually produces that E0 plus 1, right? The beta minus and electron capture are your difficult ones. So put it on a note card, do whatever you need to do to tell them apart because you'll probably see it on the test in a week or so. All right. Um, all right. So notice your book points this out that your beta plus and your electron capture can produce the same daughter nucleus. Just for example, let's say I start with cobalt 56. I can have 2 things. I can have it decay by beta plus. So remember, this is going to decay to something plus an E0 +1 plus a neutrino. You can think about what that's going to be. What are the values for A and Z as they sit over here? And then my electron capture will work similarly, except here I have an electron that's operating on this side, and you'll find that the daughter nucleus here will be the same as the daughter nucleus here. All right. What's my atomic notation for this daughter nucleus? What's in the top? Right, it's going to be 56, because I have 56 here, 56 and 0 there, so I have to add up correctly. And on the bottom, the atomic number? That's right, 26. So it's going to be the 26th element in the periodic table is iron. So I have Fe. And you can find that in the electron capture, the exact same thing happens. 56 plus 0 is 56. 27 minus 1 is 26. And so that's going to be iron. You'll also have, with the electron capture, a neutrino that'll be emitted. Okay? I can tell those apart? Okay? All right. One more. It's pretty easy, though. Gamma decay. Gamma decay doesn't actually change the daughter nucleus from the parent nucleus. You get the same thing. You just have one that's in a lower state. So an unstable nucleus, this is gamma decay. We use the Greek letter gamma, looks like that, to represent gamma decay. You will see that on the test, because that's how we represent a gamma ray or a gamma ray. It's not a particle. This is actually a part of light, the high end of the EM spectrum. No change or an unstable nucleus. Emits a gamma particle or a gamma ray. No change in mass or charge. So A and Z remain the same. We'll often mark the parent nucleus as being unstable, or they call it metastable. So, for example, if we have I think this is technetium. Let me double check that. The 43rd. Yeah, technetium. If I have technetium in a metastable state, I call it 99M. That's 43 protons. M means metastable. That means that it's radioactive, it's going to decay, but it undergoes gamma decay. So you still get technetium. It still has 99 nucleons and 43 protons, but it's no longer in that metastable state, and so it emits a gamma ray. They use technetium for medical diagnostics, radiopharmaceuticals, they call them. You've heard of this. Radioactive pharmaceuticals, they inject them into your body. They go to a particular organ, and then they can take detectors and detect that radiation and find out things about what's going on inside of your body. So this is used for medical diagnostics. You inject the metastable state. The element goes to your organs. And emits a gamma ray. And then they use detectors to detect those gamma rays. Alright, I have a little video I want to show you about this. I'll give you all just a second to write this down. And then we'll be basically done. I want to give you a few more examples. No, I don't even think I need to do that. Let's watch this video and then I'll let you go. I'll send you out. I have this little table as examples. But it's stuff that we've already covered. I'll send it out so you can look at it as you study. Y'all feel comfortable with this? Feel okay with it? Read through the chapter. It's not that much of the chapter really. We left a lot of the hard stuff out. Let's watch this video.